Okay, solar system. All right, what is a solar system? It's a star. In this case, our star would be the sun, and anything that orbits around it. All right, we have scale for size, so you can kind of see how the 4 inner planets here equate to the 4 outer planets in terms of size. And there's the edge of the sun right there, just for reference. And we also have scale for distance. So this is the sun down here. Here's our 4 inner planets right here, and then Jupiter, Saturn, Uranus, and Neptune way out here. So you can kind of see. Gives you this little perspective that Saturn is actually twice the distance from the sun that Jupiter is. It's a big distance right there. All right, so our inner planets are known as the terrestrial. The word terrestrial means Earth-like. All right, generally speaking, rocky in composition. They're solid, smaller, and more dense. Outer planets, Jovian. Jovian is a word that means Jupiter-like. You hear them called the gas giants. All right, reason is because they're gaseous. They don't have a solid surface. They're larger. Because they're gaseous, they're less dense. We think that there may possibly be solid cores down in the center, but we're not 100% sure. But there's no surface that we can speak of. It's hard to tell where the surface ends and the atmosphere begins. All right, here's the page out of your reference table, 15. This gives you a bunch of different data. Let's see, I'm going to do blue over here. All right, so here's our distance in millions of kilometers. So Mercury is about 58 million kilometers from the sun, whereas Neptune is 4,500 million kilometers, which really is 4.5 billion kilometers away. So these three right here are more than 1 billion kilometers away from the sun. All right, more than 1 billion. Okay. Notice, real quick, the moon is the same distance from the sun as the Earth is. Because at this scale, they don't differentiate the moon from the sun. At this scale, they're essentially the same distance away. But you can see they do tell you that it's actually 0.386 million kilometers from the sun. That means it's 386,000 kilometers from the sun, which, if you do miles, it's around 250,000 miles, 240,000 miles or so. Okay? Here's our period of revolution. That's how long it takes to go around the sun. Notice Mercury is about almost the equivalent of 3 Earth months. So Mercury is whipping around pretty fast. Mercury goes around about 4 times in the amount of time it takes Earth to do 1 time around. And then eventually when we get to the outer sphere, notice it changes to years. Okay? Neptune takes about 165 years to get around the sun. You guys are, 14, 15, 16 years old. So that means that Jupiter has gone around the sun only once in your lifetime. It takes about 12 years for Jupiter to go around the sun, so it's working on 2 times in your lifetime. All right. Period of rotation, how long it takes to spin at the equator. Notice the sun does have a rotational speed, right? About the same as the moon, by the way. Here's our Earth. There's where we get our 24 hours. If you want to be technical about it, they've got it listed as 23 hours, 56 minutes, and 4 seconds. All right? 24 hours, close enough. Mars is just slightly longer, all right, which means Mars rotates slightly slower than we do, just slightly slower. It takes them about, almost 37, 40, 38 minutes longer, 40 minutes longer than us to get around. Notice Jupiter takes less than 10 hours to rotate once. That means Jupiter is spinning super fast and super fast. Saturn, almost the same. Okay? These guys are all measured. These are all less. These rotational periods are all less. So that means that 4 outer planets are all spinning faster than we are. Something interesting here, remember this? Venus takes longer to spin one time than it does to go all the way around the sun. So that means that and we'll come back to that 1AU in a second. That means that Venus's day is actually longer than its year. I think that's kind of an oddball. All right. Backtrack for a second. We talked about earlier, 1AU is the distance from Earth to the Sun. So 1 astronomical unit is almost 150 million kilometers. That's where that number comes from. Okay. All right, eccentricity. Eccentricity is how out of round the orbit is. If you have a perfect 0, which would be 0.000, then you would have a perfect circle. If you have a 1, that is a straight line. Everything is in between those two numbers. All right? Venus is almost 0. It's 0.007. So it is the most circular. And Mercury is the most elliptical. Because Mercury has the highest eccentricity. But all of them are still pretty low. Oops, backtrack, sorry. Equatorial diameter. See where our largest planets are. Okay, Jupiter, distance across, as opposed to Mercury, our smallest. Mercury's not much bigger than the moon, you can see. Mass-wise, we use the Earth as our reference point. Remember, they can fit 333,000 Earths inside the Sun. You can fit 318 Earths inside Jupiter. Okay, so you can compare them that way. And then finally you can see the densities. Our gas giants have a lower density than our terrestrials, and the lowest density is Saturn at 0.07. It has a density that's actually less than water. All right, a couple different competing models of our solar system. We got the geocentric. The Earth is stationary at the center. We've got kind of a weird thing going on here, all right? There's this thing out there called retrograde motion where it looks like periodically different planets kind of back up in their orbit. Well, we know they don't back up, but back then they had, this is year 100, they were trying to figure that out. And so Ptolemy came up with this thing called the epicycle. And what he thought was that it was kind of spinning on a separate orbit, which was sitting on the bigger orbit. And that explained everything, and everybody was happy for 1,400 years or whatever. Until finally Copernicus came up with his heliocentric, right? Helio means sun, geo means Earth. And he said, no, the Earth is not the center, the sun is at the center. And this was his, and we also know now what explains the retrograde motion, or the apparent backwards motion To give you an example, we've got Earth and Mars here, okay? It has to do with your perspective. If we're in position 1 and we're looking at Mars in position 1, we can see Mars against a backdrop of stars. And because we're closer to the sun, we're moving faster in our orbit. So we catch up to Mars and pass it on the inside, so to speak. And as we're passing it, our perspective changes, and we see it appear to move backwards in its orbit when it's really not moving backwards. It's just we're going by it at a faster pace. It's an optical illusion. Right? All right, so here's kind of our geocentric orbit. We got the Earth at the center. Okay, we've got the Earth, or the Moon, the planets, all going around Earth, and then they also have their little epicycles, and that explained the retrograde motion. Notice we don't have Uranus or Neptune. They had not been discovered yet. And still, even 1,400 years later, 1,400 years later, they still had not been discovered. But we do have a better model. We had the sun at the center. The only thing wrong with this one is that Copernicus put the orbits as perfect circles, and we know now they're not perfect circles. It was discovered by Kepler that the orbits were actually ellipses. Right? We call Kepler's model the second version of the heliocentric model. So a little over, a couple hundred years later, 100 years later, Kepler published his laws of planetary motion. The first law was he discovered there's an elliptical orbit. And in an elliptical orbit, sometimes the planet is closer to the sun and sometimes it's further away. Those two terms are called perihelion and aphelion. When the sun, which is the focus, is closer to the planet, or when the planet's closer to the sun, that's perihelion. When it's furthest away, that's aphelion. It's not like a circle where there's a center point and there's a diameter. This has kind of two center points, two focal points in the center, and we end up with what's called a major axis and a minor axis. Maybe the minor axis runs this way, but we don't care about that. All we care about is the major axis running through the focal points. Right? All right, so we can measure the shape of that ellipse, something called eccentricity, from the previous slide when we looked at the diagram on page 12. The formula, the abbreviated formula, E equals D over L, that comes from our formula right here. Eccentricity is the distance between the foci divided by the length of the major axis. All right. I use the abbreviation E equals D over L, where D is from here to here, and L is all the way across. All right? And remember, our answers, when we get them, are all going to be a number between 0 and 1. It's going to be some kind of decimal, because D is always going to be smaller than L, so the top number is always going to be smaller, so we're always going to have a fraction, a decimal. All right? So there's D. There's L. Do a little measuring. Distance across from focus to focus, D, is 8.7 centimeters in this particular instance. All the way across from aphelion to perihelion, we're looking at 12.5 centimeters, so we divide that out. We get 0.697. We always round eccentricity to 3 decimals, and we always eliminate the unit. Centimeter on top, centimeter on the bottom, they cancel. Okay. No units for eccentricity. All right, where would this fall in our scale from 0 to 1? Right about there. Okay. Anything more than a 0.500, we say, generally speaking, those are very elliptical orbits. And anything less than a 500 is a slightly elliptical orbit. And if you remember, the most elliptical orbit for any of the planets was Mercury at 0.206. So it's going to fall right about there. Right about there. All right. So all the planets have really slightly elliptical orbits. All right. They're almost perfect circles. So what can we say? As the distance from here to here gets bigger, we're going to increase the eccentricity because we flatten out that ellipse. If we were to move these points closer together until eventually they were right on top of each other in the center, now we have a center point, and that's a circle. All right. So as we move those focal points further apart, the shape becomes more elliptical, more oval. All right, second law is the law of equal areas. Kepler found out that if you were to measure off a distance from one point in the orbit to another, whatever that distance may be, anywhere else on the orbit, if you measure that same, excuse me, not distance, correction, time. If you measure off a time frame, if you measure off the equal amount of time frame on the other side somewhere, the area inside that imaginary triangle that's created is going to be the same. So the area in here is going to be the same as the area in here and the same as the area in here if these time frames are all the same. So they've got 12 Earths here. So I'm going to say this is a month time. 1 month, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So each of those months. So each of these months, no matter where I go, it's going to give me an area that is the same. We have a short, fat triangle area here, and we have a long, skinny triangle here. But the area is the same, and Kepler figured that out. All right, third law is called the Harmonic Law. It just means the further a planet is from the sun, the longer it takes to go around the sun. It's kind of a common sense thing, all right? The further a planet is from the sun, it has a bigger path to travel. And because it's further from the sun, the gravitational pull is less, so the planet is moving slower in its orbit. So it has a bigger distance, and it's moving slower. It's going to take a lot longer. That's why we have Neptune taking 165 years to get around the sun, where Mercury takes 88 days. All right. Neptune is a lot further away, so it has a bigger path to take around, and it's a lot further, so it's moving slower in its orbit. And then just some perspective, we have Earth, all right? These are the speeds of the planets in their orbit in miles per second. So Earth's about 17-ish, 18 miles per second, which equates to about 65,000 miles per hour. So we're moving around the sun at an average speed of about 65,000 miles per hour. All right, and last but not least, Newton's law of universal gravitation. The force of gravity between two objects depends on their mass and their distance. All right, talked about this. Things are bigger, they're going to have more gravity and pull on each other better. If they're closer, they're going to pull on each other more. So things that are bigger and closer are going to pull on each other more than things that are smaller and further away. I mean, you don't need to worry about that formula, okay?